A black hole. People often imagine it as a hole torn open in space, but in reality, that's not what it is. Seen from a distance, it's no different from any other celestial body. Yet once you come too close, not even light can ever escape again. What is happening at its center, and how far has humanity come in unraveling its mysteries? 1. The birth of a black hole. A black hole is born when a massive star reaches the end of its life and collapses under its own gravity. For most of its life, a star holds its shape through a delicate balance, the outward pressure of nuclear fusion against the inward pull of gravity. But this balance does not last forever. In stars with a mass roughly 8 times that of the Sun or greater, once the fuel for nuclear fusion runs out, this fragile balance collapses catastrophically. The instant the iron core is crushed by gravity, a shockwave blows away the outer layers. This is a supernova, one of the most energetic explosions in the universe. And the core left behind after the supernova can keep collapsing endlessly under gravity, becoming a black hole. When the conditions, such as mass, aren't met, what usually remains is a neutron star, made almost entirely of neutrons. When two such neutron stars collide, they too can give birth to a black hole. There is also a theory that, within the first second after the Big Bang, regions of extremely high density formed and collapsed directly into black holes. These are called primordial black holes, though, as of today, not a single one has ever been found. A black hole is not a hole. Some may picture a black hole as a hole gaping open in space. But in truth, a black hole is a celestial body whose mass is compressed into an incredibly tiny region far from anything we'd call a hole. Every object in this universe has a minimum speed required to escape its gravity, the escape velocity. For Earth, it's about 11 kilometers per second, for the Sun, about 600 kilometers per second. For a black hole, it exceeds the speed of light, roughly 300,000 kilometers per second. And nothing in this universe can travel faster than light. That is why anything that comes too close to a black hole can never return. Since even light and other electromagnetic waves are no exception, observing a black hole directly is extremely difficult. The black holes discovered so far fall into 2 groups: stellar black holes, with masses from a few times to about 100 times that of the Sun, and supermassive black holes, with masses hundreds of thousands of times the Sun or more. Intermediate mass black holes, which fall between the two, have not yet been definitively found, one of the lingering mysteries of astronomy. 3. The event horizon. The event horizon is the boundary beyond which light and matter can never escape. In other words, anything that falls inside the event horizon, even light, can never come back out. According to the theory of general relativity, this means it is forever impossible to observe what lies inside the event horizon. If we imagine a black hole that is not rotating, the size of its event horizon can be calculated precisely. Its radius is called the Schwarzschild radius, and it is proportional to the object's mass. For the Sun, the Schwarzschild radius is about 3 kilometers. If there were a black hole with the same mass as the Sun, it would mean cramming the Sun's entire mass 2 times 10 to the 27th power tons into an area roughly the size of central Tokyo, stretching from Tokyo Station out to Tokyo Tower, the Tokyo Dome, and the Sumo Hall. The event horizon, however, is not like the surface of a celestial body. There is no wall there, and it does not represent the black hole itself. If you were to cross the event horizon, you would most likely feel nothing at all. For what happens if you approach a black hole? You might imagine that a black hole swallows everything. But in fact, as long as you don't get too close, it behaves just like any other celestial body. For example, if you replaced the Sun with a black hole of exactly the same mass, the orbits of Earth and the other planets would not be affected at all. So what happens if you do get too close? This depends greatly on the black hole's mass. If it were a low-mass stellar black hole, you would meet a grim fate long before reaching the event horizon. Suppose you approached feet first, the difference in gravity between your feet and your head would grow larger and larger, until it eventually tore you apart. For a typical black hole of about 5 solar masses, at a distance of 20 kilometers from the center, about 5 kilometers from the event horizon, even a difference of just 1 millimeter would create a gravitational difference 17,000 times the gravity of Earth. Shredded far too finely for the word pulverized to capture, your remains would stretch into a single thread, vanishing into the black hole. This phenomenon, called spaghettification, is experienced by any object that ventures too close to a black hole. For a supermassive black hole, on the other hand, the difference in gravity across distances at the event horizon is only slight. You would cross the event horizon without feeling a thing, and at last step into the interior of the black hole. From this point on, you can never escape, and it is theoretically impossible to send any information to the outside. All that remains is to drift toward the singularity said to lie at the center. 5. Predicting the inside of a black hole. In modern physics, the widely accepted theory of gravity is Einstein's theory of general relativity. What predictions can this theory make about the interior of the event horizon, a place we can never observe? First, inside the event horizon, the nature of space-time is thought to change dramatically from the outside. This is often described as time and space swapping roles, but more precisely, the direction toward the black hole's center becomes as unavoidable as the forward march of time is on the outside. Normally, you cannot stop the flow of time or move against it. In the same way, inside the event horizon, you cannot avoid moving toward the center. No matter how you move, general relativity predicts that you will ultimately reach the singularity. 6. What lies at the center? So what lies at the center of a black hole, that unavoidable destination in modern physics? It's no exaggeration to say that the answer is completely unknown. According to general relativity, there exists something called a singularity, and by calculation, its density is infinite. Yet many scientists believe this simply means that general relativity breaks down near the center of a black hole, and that a new theory of gravity is needed to replace it. Predicting the nature of the singularity, with neither observation nor established theory, is extraordinarily difficult. Even so, in recent years, new theories have been actively researched. One famous example is loop quantum gravity. According to this theory, time and space have a smallest unit that cannot be divided any further. This makes it possible to avoid the result that the singularity's density is infinite. Furthermore, in this theory, space-time continues beyond the singularity, and some physicists believe it connects to a white hole. In other words, matter that falls into a black hole, after being crushed, would be spat out in a different place in space-time, or perhaps into an entirely different universe. Of course, no such observation has ever been made, but loop quantum gravity is seen as a promising successor to general relativity. There are also theories arguing that general relativity is insufficient not only for the singularity, but even for the event horizon itself. One of these is the fuzzball hypothesis from superstring theory. In superstring theory, everything in the universe arises from the vibrations of tiny strings. If a black hole is thought of as a tangled cluster of these strings, the problem of the singularity can be resolved. Still, since observation is nearly impossible, humanity is likely a very long way from solving the mystery of the singularity. 7. From theory to reality: a history of observation. For a long time, black holes were nothing more than theoretical objects. Soon after general relativity was published, it was understood that, on paper, a body from which not even light could escape could exist. But whether such a thing truly existed remained entirely unknown. Time passed, and in 1964, a source of intense X-rays was observed near the constellation Cygnus. Then, in 1971, a nearby star was found to be wobbling. This revealed that the star was orbiting something that could not be seen by light or any other electromagnetic waves. Calculated from the star's mass and orbital period, the mass of this invisible object exceeded the theoretical limit for a neutron star. An unobservable object, with dozens of times the Sun's mass, that was not a neutron star today. It is almost certain that this object is a black hole. As time went on, in 2019, humanity finally succeeded in photographing a black hole, something whose very shape should have been impossible to see. The image was captured by the Event Horizon Telescope. By combining multiple radio telescopes around the Earth and treating them as a single giant telescope, it achieved extremely high resolution. The first black hole ever photographed lies at the center of the galaxy M87, about 54 million light-years away, a supermassive black hole with about 6.5 billion times the mass of the Sunday. Its Schwarzschild radius is a staggering 18 billion kilometers. The image showed superheated gas orbiting around a pitch-black point at the center, exactly as the theory predicted. At first, its very existence was doubted. But today, almost no astronomer questions that black holes are real. 8 remarkable black holes. Black holes exist in great numbers across this vast universe, and many have actually been observed. Let me introduce a few of the most remarkable ones. Gaia BH1 is known as the closest black hole to Earth ever confirmed. It lies about 1,560 light-years away, with a mass of 9 to 10 times that of the Sunday. It forms a binary system with a star of nearly the same mass as the Sun, the two quietly orbiting each other at roughly the same distance as that between the Sun and the Earth. What draws astronomers' attention is how quietly this black hole exists. It is not actively devouring the surrounding matter, nor has it formed an accretion disk, so it emits almost no strong electromagnetic radiation such as X-rays. In the words of the researcher who discovered it, place this black hole where the Sun is, and place the Sun where the Earth is, and you would have this binary system. Normally, the supernova explosion that precedes a black hole's birth would make it difficult for such a calm, orderly binary system to survive. And yet, in reality, it exists. Perhaps there is still much that humanity does not understand about how black holes are born and how they evolve. Another example comes from the James Webb Space Telescope JWST, which began observations in 2022, capturing images of galaxies from the distant past. Because the speed of light is finite, the farther away a galaxy we observe, the further back in time we are seeing. Among the galaxies JWST observed, some existed only about 700 million years after the birth of the universe. And even at that early point, their centers already held supermassive black holes disproportionately large for their size. Before this discovery, it was believed that in the early universe, supermassive black holes and galaxies grew together, but JWST's observations have forced a major revision of that idea. Did supermassive black holes grow remarkably quickly in the early universe, or did such black holes not grow from stellar black holes at all, but instead form from the very beginning as massive black holes? In the question of how this universe came to take its present form, the role played by black holes is immense. 9. The death of black holes, and the fate of the universe. Whatever is swallowed by a black hole can never escape. This, as I mentioned earlier, is what general relativity predicts. And yet, in reality, even black holes themselves are not eternal. They are thought to eventually evaporate. According to a theory proposed by the physicist Stephen Hawking, a black hole gradually emits electromagnetic radiation, slowly losing energy, until at last it disappears. But this process is extraordinarily slow. For a stellar black hole to evaporate this way would take 10 to the 67th power years. For a supermassive black hole, it is predicted to take 2 times 10 to the 100th power years. Considering that the current age of the universe is about 10 to the 10th power years, you can see that black holes vanish from the universe over spans of time almost beyond comprehension. In the leading cosmological models, stars will disappear from the universe long before black holes evaporate. As star formation consumes gas, and supernovae heat and scatter it away, it becomes harder for new stars to be born. By then, the universe will have become a far darker, lonelier, and almost unbearably vast place. In a universe without stars, the last hope for life may be black holes themselves. Life requires energy. And it has been theoretically shown that energy can be extracted from a black hole by throwing an object near it and splitting part of it away to escape. Your distant descendants may be living quietly around a black hole, as the very last life in the universe. And in the far future, when even that black hole has evaporated, the universe will hold next to nothing at all. That's all for this episode of Wonders of Space. Until we meet again.